Thank you, Aaron. Okay, I think it's pretty well known that microbiome organisms accomplish cooperative metabolic transformations that no one organism in the community can perform. And so there was an example of this that hit the news media roughly a year or two ago, which is trimethylamine and oxide, which is linked to a higher cardiac risk. And it's created through metabolic transformation of L-carnitine, which is found in red meat. And so we set this out as an example for an algorithm we wanted to develop to ask what organisms can accomplish this transformation and using what reactions. And so a little more precisely, the problem we're trying to solve is to predict metabolic transformations in a microbial community or a community of any organisms. And so we've developed an algorithm called MORS for multi-organism route search that's given it as its starting points a starting metabolite, an ending metabolite, and a set of organisms in the community of interest. And its goal is to find an optimal multi-organism linear metabolic route from the starting compound to the ending compound. And my series of arrows here at the bottom demonstrates an example route of 5 reactions that converts a starting compound to an ending compound. And the colors are meant to highlight organism switches, where there are no 2 organisms in common between the organisms that catalyze the first 2 reactions and the organisms that catalyze the next 2 reactions. And similarly, there's an organism switch between the 4th and the 5th reactions. So there are no organisms in common between those 2. Now, we built the MORS algorithm by modifying an earlier algorithm that we developed that's been part of BioCyc and Pathway Tools for a number of years that we called RouteSearch. And it's pretty similar, but it's basically a single organism version of the multi-organism RouteSearch. Again, the user specifies a starting compound and an ending compound, and they specify one BioCyc metabolic database that provides the reaction network for searching. And again, the software computes a minimal cost path from the start to the end compound. And the optimality criteria that it's using, that it's minimizing, are the number of reactions in the resulting route, the number of atoms that are lost along the way from the starting compound to the ending compound. So it wants the route to conserve as many atoms as possible, because it's quite possible to develop routes that conserve no atoms. And it does that based on atom mapping information, which I'll explain in just a minute. And it also tries to minimize the number of reactions that are foreign to the organism, because actually another option is the user can optionally allow the route search to draw from our MetaPsych universal reaction database. And so this algorithm was developed more for metabolic engineering applications where you want to minimize the number of new reactions that you're engineering into an organism. And we use the branch and bound algorithm that's published in the publication listed here, and it's been available in BioCyc for a while. So what's an atom mapping? Well, an atom mapping is basically a correspondence table between every atom in the reactant compounds for some reaction and every atom in the list of product compounds. So it maps each atom from, okay, my pointer's not working here. It maps each atom from a reactant compound to the destination atom in the product compound. And we also published an algorithm for computing atom mappings a number of years ago. And our latest version of MetaPsych contains atom mappings for almost 13,000 reactions. And then we project those mappings to other databases in BioCyc as well. What's BioCyc? BioCyc is now a collection of 13,000 pathway genome databases where we take a sequenced genome and run it through a computational pipeline where, among other things, we predict its metabolic reactions and its metabolic pathways. And we divide the organisms into 3 different tiers to reflect their quality levels. Some of the highest quality databases have received several person decades of curation, like MetaPsych and EcoPsych. And then the tier 2 databases have received generally less than a year of curation. Overall, BioCyc has been curated from 66,000 publications. And there are about 1,400 microbes from the Human Microbiome Project that are within those 13,000 databases in BioCyc. And here's a summary of the HMP body site data in BioCyc. So there are, the GI tract, of course, has the largest number of organisms, total of 480. And it also happens to have, by just a little bit, the largest number of reactions. So we've computed the union of the number of reactions present in all these different body sites, so you can see which body sites have the greatest metabolic capabilities. Okay, so how does the Moore's algorithm work? Well, it's a pretty straightforward extension of the RouteSearch algorithm, where we've basically added two things. We've added the ability for the user to specify a set of BioCyc organisms rather than just one organism, and they can either point and click at all the organisms they want to add to their set, or they can select from defined sets like all the gut microbiome organisms, all the skin microbiome organisms. And then we've added one additional optimality criterion to the list that I showed you before, which is to minimize the number of organism switches. So I want to clarify that we are ignoring transport because we're assuming that we can't predict transported substrates accurately enough that if we did try to use transporter information, we'd be cutting off so many routes that we would not be finding many solutions. Yet we still want to minimize the number of organism switches on the assumption that transport could inhibit certain routes from working, and so the fewer switches we have, the better. And then one implementation issue we dealt with was how to quickly compute the reaction sets for thousands of organisms, because to open a single BioCyc database takes about half a second. So if we were to try to open 1,000 databases, that would take 15 minutes, which is a little bit long. So we developed a optimization that relies on a special property of BioCyc, which is that when we create a new BioCyc database and we infer in that database the presence of some reaction, we give that reaction the same unique identifier in that BioCyc database as it got in every other Metacyc database. Sorry, in the Metacyc database. So the same reaction always has the same identifier. And so that property allows us to pre-compute a bit array that basically gives us a 1 when a given BioCyc database has a given reaction in it, and lets us very quickly figure out for a given organism set what reactions are present. And so when we run the algorithm on this example reaction to find a route from L-carnitine to TMAO using the gut microbiome plus humans, it finds the known route in the literature in 5 seconds. This route is shown at the bottom of the slide here. It retains 4 atoms. The first reaction is catalyzed by 79 different microbes in BioCyc, and the second reaction is catalyzed by humans only. It also finds a second known route that's been published in the literature that's more hypothetical, consisting of 6 reactions. Happy to take any questions you might have.
Thank you, Peter. We have time for a question as the next speaker sets up.
Really clever. I'm curious to see more examples. So have you taken a look to see how often you can avoid versus how often you need a switch between organisms?
Yeah, it turns out this switch capability we've just implemented in the last week at a reviewer's suggestion, or the reviewer's suggestion was close to that. So we don't have a lot of experience with it yet. We do have another example we've looked at with which is indoxyl sulfate and tryptophan. And we have a third example we've looked at too, but unfortunately we haven't had that much time to explore it yet. Thanks.